How are you, everyone? So my name is Ismael. I'm one of the co-founders of Lagrange Labs. So for those of you who are not familiar with our work, we focus primarily on building proof constructions and vector commitments that make it efficient to verify large-scale queries over blockchain data. So as some basic background, what is a vector commitment? You can think of a vector commitment as a scheme where a prover computes some succinct digest D of a vector of values and proofs for every indice such that a verifier with digest D and a proof can compute the correct value and prove the correct value of some element at some index I. And so an example of a vector commitment is a Merkle tree or a Reccle tree or an MPT tree or any structure you can think of for encoding some vector of values with ordering. Now, what is a batch proof? A batch proof is a single proof that opens k arbitrary elements within a vector commitment simultaneously. And we can think of a naive batch proof simply in a Merkle tree as a proof that concatenates the paths of individual membership proofs such that you can compute across some set of elements their inclusion within the original digest D. Now, what our team principally works on are alternative vector commitment schemes that are more performant for very specific use cases in the blockchain context. So at SBC last summer, our team presented Recproofs, which is a recursive vector commitment built around recursive SNARKs that can be instantiated on top of a Merkle tree. And so some recent work that our team has moved forward with involves what we call Reckle Trees, which are a natural extension of Recproofs to instantiate data structures that have many of the fundamental properties of Recproofs, but can be used to encode and compute very large queries over that data. And so what makes Recproofs and Reckle Trees very special? So the main differentiation of Reckle Trees is the fact that they are updatable. You can construct batch proofs of computation over some subset of elements within a digest, and then update those batch proofs as either the digest changes or the subset that you're computing over changes. And the core of how this is done is an algorithm that our team has proposed called canonical hashing, which allows us to represent in a deterministic fashion the set of elements contained within a given branch node, or contained below a given branch node, in a way that every proof can assert the inclusion of the set of elements contained below it. And so as we kind of propagate up this data structure designed with recursive arguments, we're able to construct a final batch proof that asserts the inclusion of all of the elements contained below. And when one element changes, all we have to do is update the corresponding canonical digests from the leaf that has changed all the way to the root, such that we can, in logarithmic time, update the overall batch proof. Now, so we're going to discuss today some performance numbers of how Reckle trees perform compared to naive approaches. And so we've discussed performance numbers of our Recproofs construction previously, but these are some new numbers that our team has put forward over the overall data structure based on some more recent optimizations. And so the three areas that we've assessed for comparison with respect to the naive approaches are proving time, update time, and verification time, or aggregation time being proving time. And so what we've found is that across the board, Reckle trees outperforms the naive constructions on all three of these heuristics for very large batch sizes. The main thing that Reckle trees possesses that a lot of these naive constructions don't is that it's fundamentally parrelizable, that we can in essence throw more machines at computing Reckle trees, and we can scale the efficiency with respect to the amount of compute that we throw at it, obviously minusing any networking overhead. And so for proving, as compared, let's say, to the original Recproofs paper that we positioned at SBC, we were 37 times faster with the most recent Reckle tree construction. Compared to both the naive approaches, hyperproofs and Merkle SNARKs, hyperproofs being a vector commitment scheme designed by some members of our team previously, and Merkle SNARKs being just batch proofs over Merkle trees, we were 1.6 and 2.1x faster, respectively. Where Reckle Trees really is fundamentally different is on updates. And this is what I was talking about earlier over one of the core principles and the core properties of Reckle Trees. And so compared to the naive approaches like hyperproofs and Merkle SNARKs that don't have native updatability, Reckle Trees is 11 times faster and 15 times faster, respectively. Compared to the previous work that our team has done with Recproofs, the Reckle tree construction is 2.1 times faster. And so across both proving and aggregation and updates, we're faster across the board. And these were done for large batch sizes of up to 2 to the 27 in terms of the size of the tree. So our team has also proposed in the Reckle tree paper a very recent, a very actually interesting extension of Reckle trees, which we call Reckle plus trees in homage to B trees, or B plus trees. So in Reckle plus trees, a prover commits to some memory M, and then prove the correctness of both the inclusion of a subset of M and then a map or reduce computation over that subset. And so you can think about this as a natural extension where the recursive arguments don't just compute the canonical digest, but they also compute the computation over the subset of elements contained within that canonical digest. So you, in essence, accumulate both inclusion and computation as you propagate your proofs up the tree. And we've positioned a number of applications for this in the Reckle tree paper, but the core one that is very relevant in the blockchain context is something called digest translation. And digest translation is what our team believes to be the foundation of building verifiable databases on major blockchains. And so what digest translation allows you to fundamentally do is to assert the equivalence between one digest D and then another digest D prime that's a subset of D. And these digests can be constructed with different hash functions and different serializations such that you can have a proof of equivalence that enables you to compute over the second digest or query over the second digest and then assert its equivalence to the first digest. Which means that if you have a piece of data on chain that you frequently need to compute over a query, you can do so without having to compute over SNARK unfriendly structures every time you want to do that. And so we'll position very shortly some benchmarks of why this can really scale computation over on-chain state rather materially. But as a very basic idea, I just want everyone here to think of any application that is constrained by its ability to prove the inclusion of memory in some commitment can be extended to not have to prove that commitment within the original memory, but over some optimized memory that's more efficient or compatible with the underlying SNARK that you're using for your computation. And so, for the original digest translation that we positioned in the paper, we are faster on the verification time, same as the Reckle tree work, and we're substantially faster on both proving time and updates. So because our Reckle tree construction is parrelizable and can be distributed very naturally, and we are up to 200 times faster than the baseline on proving and on aggregation. And so another very important note to mention here is that digest translation over Reckle plus trees can extend to far larger tree sizes without reaching memory constraints than you would traditionally see if you were trying to construct this all in a monolithic circuit. And so we were able to push the kind of the boundaries of the digest translation well over 8 million elements in these sets for Reckle plus trees, and we have historically hit memory limitations when trying to do this with sequential naive approaches, whether that be hyperproofs or Merkle SNARKs. And now, with updates, intuitively, if you're updating a very, very large tree, Reckle proofs are just going to be a comically large number faster because you have to recompute the entire tree from scratch. But even with naive approaches, but even with small size trees, the update time on Reckle trees is substantially faster than recomputation. As you think about adding more expressive computation into a recursive argument on a Reckle plus tree, you're able to save even more on the delta between recomputation by just simply updating. Now, so how are we applying this in the blockchain context? So when we think about a Reckle DB, is what our kind of working name is for how we want to instantiate this on chain and how we are instantiating this on chain. It really composes two primary operations. The first is the pre-processing of a large amount of on-chain state into an optimized structure. And the second is provably querying over that optimized structure such that you can then recurse those two final proofs together, asserting in the public input that the computation is valid with respect to the original block header of the chain. So in essence, you can take a subset of on-chain state, you can generate a proof of its equivalence to an optimized structure, and then you can compute over the optimized structure as much as you want and then recurse those final two proofs together while only needing to compute the pre-processing of the transformation once upfront. And so what this does is it creates kind of a ZK-friendly database that can be structured and organized however your application wants to compute over that state later on. And so we talked about the pre-processing step, but in essence, we take some subset of the storage tree, or we can also do receipt or transaction tree on Ethereum, and we prove its equivalence to an optimized structure that removes the catch-ack hash function and removes the RLP serialization. And the optimized structure is built with either monolith or Poseidon 2, and just as a simple binary tree, which makes us able to structure computation over that at a much larger scale. And so we're going to quickly summarize the tables that we create in our Reckle DB. But the first is what we call our storage table, which is a subset of storage that you want to compute over for a given contract and a given block. This could be, let's say, an NFT mapping. It could be an ERC20 balance mapping. It could be maybe prices across a number of dexes that you would like to every block extract out of on-chain state and store in the optimized structure. Next, we have what we call the state table, which unifies the storage tables across multiple contracts in a given block. And you can just join these on the storage table to the state table, and then you can, in essence, have the chronology of the path. And so with these equivalence proofs, we once again, as I mentioned, we strip away the catch-ack and the RLP encodings, so everything's just built with Poseidon 2 or monolith, and are much faster to compute over. And then the next thing that we do is we take we create what we call the block table. And the block table is a table that proves the inclusion of a number of blocks within some range that we would like to dynamically compute over that remove the nature of sequentiality from those blocks. So if you want to compute a proof over some subset of, let's say, Ethereum state over some range from block B to B plus K, and you don't want to have to compute those proofs chronologically, wherein the validity of B plus 1 is dependent on the previous hash contained in B plus 2. So you want to be able to run everything parrelizable for all those blocks, where the linking of those blocks in the proofs can be done once again in a way that's parallel and is not sequential with respect to the ordering of those blocks in the chain. And so this is the next transformation we do, where we use a hash to curve to basically take the connection of all these blocks and hash those to an order agnostic structure, and then basically re-index those to be leaves within what we call our block table. And so when thinking about the performance of this, there are two important things to consider. There's the initial database setup and then the update of that database per block. And so the initial database setup can be done in about, let's say, 75 to 80 seconds for 10,000 or 100,000 leaves respectively. And then the update per block can be done with about 58 to 64 seconds. So this is obviously a little bit longer than block time right now, but we anticipate later versions to be able to get this sub-block time. And it's worth mentioning that with the updates, you save a significant amount of CPU time, as you can reuse the majority of the inclusion with the Reckle tree construction we discussed earlier. And so when we structure computation over this, since everything can be done parrelizable, our team targets a map-reduce inspired design, where a map being a unary function on a set where each element of the set can be processed without reference to other elements of the set, and the reduce operation, a binary function on a set, which produces a new set whose size is at max the size of the input sets. And with this very simple map-reduce framework, we can structure most SQL-like or query-like operations as a series of map and reduce operations. And we can run this all in a parallel fashion. And so by extension, we have a distributed systems architecture that does this, that allows us to get very, very parallel on everything we're doing. And so the performance numbers that we can get, that we're going to show right now, are much faster. So once you have everything in the optimized structure, the main payoff is that queries can be done at a scale that's otherwise impossible over blockchain state. And so if we want to compute over a database of size 500,000 storage slots, we can do so in about 6.6 seconds, so in roughly half the time of an Ethereum block. If we want to compute over a database of, let's say, 1 million rows, we can do so in about 8.9 seconds. And so we can effectively structure very, very large databases over both current state and historical state, which can include, let's say, the entirety of an ERC20 mapping, the entirety of NFT mappings over time, and then we can structure the computation over that to be done in even under block time. And it's worth mentioning that when you think of this type of construction, the latency on the setup of the database is not incurred by the user who wants to query it. That's in essence just a continued cost that happens every block. So you have about a 4-block delay on having the database updated. The queries that a user, for example, requests over that data are the main source of latency or DevX experience. And this is all incredibly fast as the structure has now been optimized. And so these queries were mostly done with like very simple arithmetic operations or very simple select statements. But we have some work that our team is doing on a lot more complicated unions, joins, etc. And so for those of you who want to read the paper or to dig into the code, we'll be releasing the Reckle Tree paper and the Reckle Tree code base in mid-March. And in late March, we'll be releasing the ReckleDB testnet and the first version of our MapReduce coprocessor. This will allow you to define, in essence, on-chain, the series of storage slots you want to be computed into this database, and then to have that basically be continually computed for your contracts so you can query it on demand. Awesome. So any questions?
Thanks for your presentation. You've mentioned that some, like with few exceptions, MapReduce kind of can model anything queryable. What are those exceptions? Can you speak about them? What cannot be represented in the MapReduce?
Off the top of my head, I'd have to look into that.
No worries then. It's not that important then.
Yeah.
In that case. Okay.
Any more questions? Going to take one more. I guess I'll ask a question. So
yeah.
how does this compare to the previous talk on the Hackathon? So do you do kind of any like cross subproof lookups?
Sorry, cross subproof lookups.
Yeah.
I'm not sure what a cross subproof lookup.
Never mind. If you take a look at that paper when it comes out, they're like doing some clever like subproof lookups. You have like global ROM that can be looked up across all the subproofs.
Oh, that's actually very interesting. Yeah, I mean, that would be actually very relevant to us.
Is Michael here? You should chat with him offline.
Yeah.
Okay. Let's thank Ismael.
Thanks, everyone.